Unit 5, Day 3, talking about first and second differences. In a linear relation, the first differences are constant, with evenly spaced x values. With quadratic relations, the second differences are constant, with evenly different x values. Now, what we mean by evenly different x values is that these x values are consecutive. -2, -1, 0, 1, 2. In this case, x is increasing by a constant even value of 1 each time. So we have a linear equation. It's going to be a straight line. And the equation is y equals 2x minus 4. So we're building ourselves a little table of values here. We plug the -2 in for x, and we get a result of -8. So our first coordinate pair is going to be -2, -8. Then, plugging in -1 for the x value, we're given a value of -6. Plug 0 in, we get -4. Plug 1 into the equation, we get -2. Plug 2 into the equation, and we get 0. So we have coordinate pairs of -2, -8, -1, -6, 0, -4, 1, -2, 2, 0. And if we plot these points on a Cartesian plane and draw a line through the points, we can see that indeed we have a straight line. Now, I want to look at these y values right here. What we're going to do is we're going to calculate the difference between this y value and this y value. So we're going to write a statement that says -6 minus -8 with a result of 2. Now we're going to look at the difference between these two y values. -4 minus -6 also equals 2. And then look at the difference between these two y values. -2 minus -4 equals 2. And finally, the difference between these two y values, 0 minus -2, also gives us an answer of 2. So the differences between these y values are all 2. So we say that the first difference is 2 in each case. When the first differences are constant, we have a linear relation or a straight line. We can look at the second differences where we take 2, subtract 2, gives us 0. And in each one of the remaining cases, we're subtracting 2 from 2 and getting an answer of 0. So our second differences are also constant. But with a linear equation, noting that the first difference or the first differences are all the same, that is a feature or a characteristic of a linear equation or a straight line. Now we're going to look at a second equation. This is a quadratic equation. We know it's quadratic because it's got the x squared in the relation. Once again, we have evenly spaced out x values. They're consecutive from -3 down to 2. If we take this -3 and we plug it into the equation, we end up with a result of 14. Taking a negative 2, plugging it into the equation gives us a 4. Negative 1x, x substituted in the equation gives us a y value of negative 2. And we continue on. Now we have coordinate pairs, negative 3, 14, negative 2, 4, negative 1, negative 2, 0, negative 4, 1, negative 2, 2, 4. We'll plot all these points on our Cartesian plane. We'll do that. I'll show the graph in a minute. But for now, we're interested in the first differences. So we'll take 4, subtract 14, gives us a result of negative 10. Negative 2, subtract 4, gives us an answer of negative 6. Negative 4, subtract negative 2, gives us negative 2. Subbing in negative 2 minus negative 4 gives us an answer of 2. And 4 subtract negative 2 gives us 6. Now, looking at the first differences, they are not constant. This is one of the characteristics or features of a quadratic relation. Okay? The first differences are not the same. Now, we're going to look at the second differences. We'll take negative 6 minus negative 10 will give us 4. Then we'll take negative 2, subtract negative 6. That'll also give us 4. Take this value 2, subtract negative 2, gives us 4 once again, and then 6, subtract 2, gives us 4. Now the second differences all have the same value, and this is the second feature or characteristic of a quadratic relation. The first differences are different. The second differences are all the same. So when you have this characteristic of the first difference being different, the second differences being the same, then you can say that the relation is a quadratic. And if we were to graph these points, negative 3, 14, negative 2, 4, negative 1, negative 2, so on, you would see that we get the characteristic shape of a quadratic equation, which is the parabola. Here we have a word problem. The relation h equals negative 5t squared plus 210 describes the path of a rock that falls from the top of a cliff, with h representing the height in meters and t representing the time in seconds. So what's happening here is a rock is falling, and it's being dropped from a cliff at a height of 210 meters. And every second that passes, the rock is going to fall a certain distance. So we're going to keep track of what the height of the rock is over a period of time. So here we have, over here, in this column right here, we have t in seconds. And t is going to have consecutive numbers like this. It's very important that the x values, or in this case the t values, be consecutive. And then what we're going to do in each case is we're going to plug these t values into the equation to give us the h value. And when we do that, we plug in 0, we end up with 210. which makes sense because at 0 seconds, the rock is going to be the height of the cliff. The height of the cliff happens to be 210 meters. After 1 second, the rock's dropped 5 meters, and the rock is now 205 meters. And each second passes, the rock falls further and further, and the height of the rock is a little bit less. So what we're going to do is we're going to take a look at the y values, or the h values. We're actually keeping track. H sort of takes the place of what y normally is, and t takes the place of what x normally is. So we're looking at these h values or y values, and we want to know what the difference is between each one. So we start with 205 minus 210 gives us a first difference of -5. Then we look at 190 minus 205 gives us a first difference of -15. And so on, working our way down, calculating the difference between this value and this value, this value and this value, and we end up with a series of first differences that are -5, -15, -25, -35, -45, and -55. So, because the first differences are changing, because they are not constant, it seems like we have a parabola. But just to be absolutely sure, we take a look at the second differences. So we take this -15 minus -5 gives us -10. Minus 25 subtract -15 also gives us -10. Minus 35 subtract minus 25 gives us -10, and so on and so forth. So our second differences are constant, and that is the second check or criteria that we have to make sure is happening for this to be a quadratic equation. The first differences have to be different. The second differences have to be constant. That tells us that we do indeed have a quadratic equation. All right, let's have a little bit of fun with some animations. So at 0 seconds, we have a rock that is at 210 meters. So our coordinate is seconds, height. 0 seconds, 210 meters. There's our rock sitting there at a height of 210 meters. After 1 second passes, the rock has fallen 5 meters, and we can see this point representing that fact that we're 1 second over and 5 meters lower. After the next second, 1 second has passed, the rock has fallen 15 meters this time. So in the first second, the rock falls 5 meters. In the second second, the rock falls an additional 15 meters. And then in the third second, the rock falls 25 meters. In the fourth second, the rock falls 35 meters. The rock is falling faster and faster with each second, and this reflects what happens in reality. If one is to drop a stone, at first the rock is not moving very fast, but as time passes, it moves faster and faster. At 5 seconds, the rock falls 45 meters in the last second. And after 6 seconds have passed, the rock's fallen 55 meters. And then sometime between the 6th second and the 7th second, the rock will hit the ground. This negative 35 doesn't really reflect reality. The rock is not going to suddenly be 35 meters underground. Also, this parabola doesn't really apply here because this would involve going back in time, -2, -3, -4 seconds. So that's not really a realistic approach to what a rock actually does in real life. But from here, 0 seconds to 10, all the way down to 6 seconds and 30 meters, this more or less reflects what a rock might behave like over a 6-second period. Now, let's look at our first and second differences and see how they relate to what's happening. So we've got the rock at 0 seconds at a height of 210 meters, and then 1 second later, it's fallen 5 meters and is now at 205 meters, at a height of 205 meters. The next second, it falls 15 meters in a second. And the next second, it falls 25 meters during that second. And so on, and so on, and so on. It's falling at a faster rate as the seconds pass. Now let's look at this second differences and see what that -10 represents. What this is telling us is that after every second passes, the rock is falling 10 meters per second faster than it was the second before. So, falling 5 meters per second and then falling 10 meters per second a second later tells us that it's speeding up by a rate of 10 meters per second. And then, in the next second, when it was falling 15 meters per second, but now falling 25 meters per second, again, the rate of it falling has increased by 10. So after every second, it is falling 10 meters per second faster than it was the second before. And you can see this acceleration just by looking at the distance between the rocks after each second. Here, just 5 meters per second. Here, it's falling a little bit faster. In the next second, it's falling a bit faster, until at this point, it's falling quite quickly at a rate of 55 meters per second. 10 meters faster than it was the second before. Now, some of the characteristics of a linear versus a quadratic relation in graph. The graph of a linear equation is a straight line. A quadratic equation has a graph that has this parabola shape. If you make a table of values for a linear, the first differences are the same, and the first differences are the same for a quadratic, but the first differences are different for a quadratic, but the second differences are the same. Okay. The equation of a linear does not have any exponent, and it's based on our old friend y equals mx plus b, whereas the equation of a quadratic does have an exponent, has the x squared here, and it follows the equation y equals ax squared plus bx plus c. A will be some coefficient in front of an x squared term. B will be some number or coefficient in front of the x term. And C will be a constant. It won't have any variable with it. Okay. An example of a linear, y equals mx plus b. Here we are, y equals 2x plus 4. An example of a quadratic equation would be something like y equals x squared minus 4x plus 9.